How many ways are there to tile a 1x8 block with 1x1 squares and 1x2 dominoes? Well, we could use all 8 squares, or all 4 dominoes. But there are many other different combinations, and it's not immediately obvious how to organize and count them all. This is a good chance for a classic problem-solving trick of first solving an easier problem. If a 1x8 block sounds too tricky, let's first look at smaller cases to see if we get any ideas. We will call f of n the number of ways of tiling a 1x(n) block, and work our way up to f of 8. A 1x1 can only use a single square, but a 1x2 can be 2 squares or 1 domino, and for a 1x3 we get 3 different ways to tile it. If we stopped here, we might guess that the rule is simply f of n equals n. But looking at the next case, there are actually 5 ways to tile the 1x4 block, so the pattern isn't that simple. Working out all the options for the next case, we find 8 different ways to tile a 1x5 block. At this point, we might recognize this as the famous Fibonacci sequence. Now, most people define the Fibonacci numbers as starting with 2 ones in a row. In fact, it makes sense to say f of 0 equals 1 here, because there is only one way to tile a 1x0 block. Use no tiles at all. The key recurrence that defines the Fibonacci sequence is f of n equals f of n minus 1 plus f of n minus 2. So to prove this really is the answer to the tiling problem, we need to prove that the number of ways to tile a 1x(n) is the number of ways to tile a 1x(n minus 1 plus the number of ways to tile a 1x(n minus 2. This is a good spot to pause and ponder where this recurrence is appearing in our tiling solutions. The idea is to consider the first tile in the tiling, which will either be a square or a domino. If we start with the square, there will be n minus 1 spaces left over, so there are f of n minus 1 ways to finish the tiling. If we start with the domino, there will be n minus 2 spaces left over, so there are f of n minus 2 ways to finish the tiling. The total number of tilings is split up into these 2 disjoint cases, which is why we add those counts together. We can also use this recurrence to quickly draw all possible tilings for each successive value of n. We first take all the n minus 1 tilings and add a square to the left. Then we take all the n minus 2 tilings and add a domino to the left. Repeating this process, we see f of 6 equals 13, f of 7 equals 21, and finally f of 8 equals 34 is the answer to our original question. But we didn't actually have to draw them all out to get the answer. This recurrence made it much easier to count. So the Fibonacci sequence gives the general answer to our problem. Starting indexing at 0, the nth Fibonacci number is the number of ways to tile a 1x(n) block. This gives a more tangible meaning to these numbers. What is 987? It's the number of ways to tile a 1x15 block. Often the Fibonacci sequence is described with a story about rabbits, which is contrived just to satisfy this recurrence. But you can't use the fact that there are 987 rabbits to say anything else interesting about the Fibonacci numbers. On the other hand, by reasoning about these tilings, we will be able to prove multiple identities. These tilings turn out to be a more fundamental representation, which will give visual proofs of 3 different patterns we find in the Fibonacci sequence. The first pattern comes from adding successive Fibonacci numbers. Looking at each of these partial sums, we will notice a pattern. These sums are all 1 smaller than a later Fibonacci number. Writing this pattern more concisely, we have the sum of f0 up through fk is f of k plus 2 minus 1. Now the standard way to prove this would be using induction, but our block tilings give a more direct visual proof. For that, we don't want any negative numbers, so we will rewrite this formula. Now what this identity is saying is that the number of ways to tile a 1x(n) block is the sum of the ways to tile a 1x(n minus 2 block, a 1x(n minus 3 block, all the way down to the single way to tile a 1x0 block, plus 1 more. To think about the proof, we will look back at the 34 tilings of a 1x8 block. This is a good spot to pause and ponder how these tilings can be broken up into the sum above. The key idea is to consider the first domino used in the tiling. It's either the first block, the second block, the third block, all the way down to using the first domino as the last block, or there can also be no domino at all. If we separate these cases, we see that starting with the domino, there are f of n minus 2 ways to finish, and then in general we get all smaller cases, down to f of 0 ways to finish if the last tile is a domino. The extra 1 comes from the case where there are no dominoes at all. So these partial sums were hiding right in the way we had organized our list of tilings. The next identity comes from looking at Pascal's triangle, where each entry is the sum of the two entries above it. We will look at the sum of entries across slanted diagonals in Pascal's triangle. Surprisingly, the Fibonacci numbers pop out. So our 34 tilings are the sum of one of these diagonals. Since the kth entry in the nth row is n choose k, we have the sum 8 choose 0, plus 7 choose 1, plus 6 choose 2, plus 5 choose 3, plus 4 choose 4. Now we want to see how our 34 tilings can be broken up into this new sum. This is another good spot to pause and ponder how else we can split up these tilings. The idea is to consider tilings with 0 domino, 1 domino, 2 dominoes, 3 dominoes, or 4 dominoes. With no domino, there is only one tiling with all 8 squares. With 1 domino, there are 7 total pieces, and 7 choose 1 equals 7 ways to pick which piece is the domino. Then with 2 dominoes, there are only 6 pieces, and 6 choose 2 equals 15 ways to pick which 2 pieces are dominoes. We similarly have 5 choose 3 equals 10 ways to choose where to put 3 dominoes, and then 4 choose 4, giving only one option for how to have all 4 dominoes. Our last identity comes from looking at sums of squares of adjacent Fibonacci numbers. Looking at small cases, we see this always gives another Fibonacci number. Tracking which one it is, we have that f of n minus 1 squared plus f of n squared equals f of 2n. As usual, we will look at f of 8, where the 34 ways to tile a 1 by 8 block is equal to the 3 ways to tile a 1 by 3 squared, plus the 5 ways to tile a 1 by 4 squared. Again, this is a good place to pause and ponder where this third equation could be hiding in our 34 tilings. The key idea is how to interpret the squared numbers. Squaring the set of 3 1 by 3 tilings counts all 9 ordered pairs of tilings, and squaring the set of 5 1 by 4 tilings counts all 25 ordered pairs of tilings. So we need to show that together, this gives all 34 1 by 8 tilings. The ordered pairs of 1 by 4 tilings have a natural interpretation as the left half and the right half of a 1 by 8 tiling. As long as the tiling is able to be split down the middle, we can decompose it into 2 separate 1 by 4 tilings in this way. But there is one other case to consider, where a domino exactly comes across the middle like a band-aid. In this case, there will be 3 empty spaces on the left and 3 empty spaces on the right. So the other 9 cases are the different pairs of options for how to tile the left and right halves if the middle piece is a domino. As a bonus problem, see if you can think how you might generalize this argument about splitting the tiling into 2 pieces, if you don't happen to split right down the middle. This will let you use an argument about tilings to discover your own new identity within the Fibonacci sequence, which will have this sum of squares as a special case. So by looking closer at our original problem of counting the 34 ways to tile a 1 by 8 block, we find explanations of multiple different structures hidden within the Fibonacci sequence.